Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We have been going through a course of lectures on semiconductors, and today we will have the lecture number 14, which forms part of the paper on physics of materials. And in this lecture we will be talking about the formation of potential barrier and the width of the depletion region in the PN junction, and ultimately we have to obtain what is called the rectifier equation, which will be of great significance as the junction diode can be used as a bridge rectifier. And the contents of today's lecture are as follows: expression for the width of the PN junction, extension of the ionic layers in the neighborhood of the PN junction, and the junction diode equation, which will be ultimately obtaining using the mathematical expressions we will come across. Now, we have started with silicon or germanium, the basic semiconducting materials. Then we doped them. What kind of doping? You either add pentavalent impurities and make the semiconducting material to become a N type semiconductor, which will donate electrons, or else you add trivalent impurities to the silicon or germanium to get what is called a P type semiconductor, where you create more number of holes. P refers to positive, positive means the majority carriers are holes. Here on the N side, the N type semiconductor, you have got electrons as majority carriers, and there will be always minority carriers. In the case of N type, the majority carriers are electrons and the holes are minority. On the other hand, in the P type, it is the reverse. Holes are majority and the minority carriers are electrons, which are, for the sake of convenience, they are not shown. And when you have got excess carriers on this side or that side, then what will happen is there will be flow of carriers, like thermal diffusivity, wherein heat flows from the high temperature end to the cold temperature end. Similarly, here you have got excess electrons in this region, deficiency electrons or the minority carriers the electrons here, there will be smaller number of electrons. So, the electrons will flow from here to here and holes will flow from the left to right, and finally you will come across an equilibrium state, during which state or after this equilibrium is obtained, in the junction region you will be having only what is called the depletion region, that is a set of ionic layers, or in this region you will not be having free carriers. So, it is called depletion region wherein you do not have free carriers, or it is depleted of the free carriers, that is the reason why it is called depletion region. And you may ask the question whether the depletion region will be symmetrically extending on either side. You see here I have put 2 ionic layers, positive ionic layers on this side and 2 ionic layers on this side, and you may have to ask me or ask your teachers to explain to you whether the extension of the ionic layers will be symmetrical, or to what extent will it be extending to a large value or it will become small. So, these are the things which we will be dealing with today, or the width of the junction region, the width of the ionic layers is called the width of the depletion region, which we will be talking about today. The kind of mathematics, what is the mathematics? But now the electron which you have here will try to go to this side, then in such a case it will has to overcome the repulsive potential exhibited by the presence of negative ions. You see that you have got a negative ions, these negative ions will exert a repulsive potential on the electrons when the electrons try to go from this side to this side. Similarly, when a hole comes here, the hole also will experience a repulsive potential offered by the positive ions on this side. Now, therefore, in either case whether it is the electron or the hole, they have to overcome a potential barrier, and so we will be looking at the potential profile which we saw in the last lecture, and what the shape of the potential profile will be looking like this. What I mean by this, if you have got a particle here, that particle it may be electron or a hole, it has to overcome a barrier, right, a barrier theta naught in order to go from this region to this region, and similarly for a particle from here to here also it has to overcome a potential barrier on the same thing. You can have a mirror reflection irrespective of the case whether it is an electron or the hole, it has to overcome a potential barrier, and in some cases the junction will act as a potential well. For the minority carriers it will be a potential well, and in the course of the lecture I will explain to you what is meant by a potential well also. Now, I am showing a potential barrier. By potential barrier what I mean is a repulsive potential, it has to overcome a surmount a potential barrier. Something like the potential barrier is something like what you have when you go in a car, you have to overcome a gravitational potential barrier. The speed breaker is an example wherein you have to overcome, you have to go climb over the barrier, right, it is a gravitational potential. On the other hand, you have got water in a well, it is a potential well, it is attractive potential, it is again a gravitational potential. The water is below the ground level, whereas the barrier I am talking about, the made up of cement on the road, it is above the ground level, or whereas the well is water in the well is below the ground level, it is called a potential well, and this is a potential barrier. Okay. What we saw in the last lecture, the potential with its reference 0 potential at x equal to 0, you see here the potential is 0 for all points x equal to 0 or less, x less than 0 for all the points the potential is 0. Now, after the depletion region the potential is theta naught, it has overcome a potential of height theta naught, and what I am trying to tell you is now the potential with its reference 0 potential x equal to 0 is called the contact potential. I call this theta naught is the contact potential, and so theta naught is what? Theta naught is nothing but theta 2 determined at x is equal to x p plus x n, that is your theta naught. Okay. Thereafter you have the theta naught, right, it has the same value. So, by substituting x equal to x p plus x n in the equation which we saw in the earlier lecture, you will come across an expression of this kind, wherein you have this theta naught is equal to minus E, that is the electronic charge, multiplied by Nd. What is Nd? The number of the donor atoms. Xp plus Xn obviously refers to the width of the depletion region, the extension of the layers in the p side, and similarly extension of layers in the n region. So, Xp plus Xn is the width of the depletion region, that divided by 2 epsilon plus your E into Xp by epsilon into Na plus Nd, and then you have got Xp plus Xn minus E into Xp square by 2 epsilon into Na plus Nd. That is the expression for the contact potential. This contact potential is of great significance, because you will be coming across this potential in the steps to come. When no external voltage is applied to the PN junction, there will be no current across the PN junction. The sum of the currents I1 plus I2 plus I3 plus I4 is equal to 0. What is I1, I2, I3, I4? I1 and I2 are the currents due to the majority carriers, whereas I3 and I4 are the currents due to minority carriers. I1 is assumed to be the whole current from the P region to the N region. What is the P region? P region contains what? The P region contains holes. So, holes are majority carriers, as all of you know. On the P side, the holes are majority carriers. Now, therefore, I1 is the whole current, that is the obviously whole current is due to the holes from the P region to the N region. Now, go to I2. What is I2? I2 is again the majority carrier current, wherein what is the majority carrier current? The other majority carrier current, the N region will contain more number of electrons. So, the electrons on the N region will go to the P side or the P region, that is I2. So, I2 is the majority carrier current. So, if Pp is the equilibrium hole density in the p type material, only those carriers whose energy is equal to or greater than E theta naught, only those electrons will go to the other side. So, the current that will be flowing from the p type material to the n type material, I am talking about the majority carrier current, that will be given by a constant, it is a constant of proportionality, that is C1 among the Pp holes. What is P? P is the number of holes and P is the type of material, and the barrier height is E theta naught, theta naught is the barrier height. So, the probability, how do you get the expression? It is something like the Maxwell-Boltzmann statistics, right. Even though you are talking about electrons and holes, the Fermi-Dirac distribution will reduce to the Maxwell-Boltzmann distribution under certain limiting conditions, and so we assume those limiting conditions to be applicable here, and that is the reason why you are putting E to the power of E theta naught by kT. Only among the Pp holes, how many will be going from the P side to N side, that is given by I1 will be proportional to the number density Pp multiplied by e to the power of minus E theta naught by kT. Then because I am telling proportional, the C1 will be the constant of proportionality, right. Similar is the case for I2. I told you what is I2, the majority carriers on the N side are electrons. So, the majority carriers on the N side will try to go to the P side. So, this is the majority carrier current I2, which tries to flow from N side to the P side. Therefore, I2 is the electron current from the N region to the P region. If Nn is the equilibrium electron density in the N type material, then similar to the earlier equation that we saw just now, we can write a corresponding current contribution as I2 will be equal to again another constant of proportionality C2. Nn is the hole density in the N region, okay, the hole density in the N region into e to the power of minus E theta naught by kT. So, this is the current due to the electrons, electron current flowing from the n region to the p region. Now, the other two contributions are I 3 and I 4, they are the currents due to the minority carriers. The majority carrier current means what? The holes flowing from p side to the n side. I 2 will be the electrons which are flowing from n side to the p side. In the n side, the majority carriers will be electrons, as all of you know. The minority carriers are holes. So, the majority carriers electrons which are flowing from the n side to the p side is given by the current I 2. The current component I 2 will be equal to a constant of proportionality C 2 multiplied by n n e to the power of minus e theta naught by k t. In the case of these two currents, one should remember they have to overcome a barrier. What is the barrier height? The contact potential is the barrier height. They have to climb up a barrier. From here, if it is electron or it may be hole, right, it has to overcome a barrier, right, the opposing barrier. That is a very important point. A particle, it may be electron or hole, as I told you, it has to climb up a barrier of height theta naught. That is important to note. Whereas, for the minority carriers, supposing you got a hole here, you have the minority carrier on the p side. What is the minority carrier on the p side? The majority carriers are p means the positive. Why do you say positive? Because the carriers are holes, the majority carriers are holes, there will be minority carriers which are electrons. So, if an electron comes in the vicinity of the depletion region or the p n junction, suppose an electron is found here, what will happen to the electron? It will be immediately be attracted by the positive ions. You see the positive ionic layers, right. So, if an electron were to come here, it will be attracted by the positive ionic layers. Similarly, n type material, the minority carriers are holes. Supposing a hole comes here, it encounters a negative ionic layers, right. You have got layers which are negatively charged. Supposing you have a hole here which is minority on the n side region, the n type material, minority carriers are electrons, minority carriers are holes, right. You have got a hole. Supposing a hole is able to come here, then the hole will be attracted, right. The hole is positively charged, the hole will be encountering number of negative ions, it will feel an attractive potential. So, for the minority carriers, the presence of the ionic layers will lead to attraction, either the ionic layers that you have got on this side or the negative ions you have got on this side. So, for the minority carriers, you should remember the junction region will act as a potential well. So, you should be able to distinguish between potential barrier and a potential well. So, I will go through the pictures wherein you will find what you should know from the potential well and the potential barrier. This is a potential barrier. Why is it called potential barrier? If you have got a particle here, in order that the particle goes to this region right, if it were to come, you assume a automobile, right, you have got an automobile, it has to come here, this is a barrier, right. On the road when you go, you have got the speed breaker, right, this is something like a speed breaker. In a case of automobile, it has to overcome a gravitational potential barrier, but for the electron or hole, you are overcoming an electrostatic potential barrier, right, this is a potential barrier. So, if the particle is here, it has to overcome go through a potential barrier. So, the potential is to be raised above this value, right, in order that it goes to the region 3. This is a, you call this the region 1, this is the region 2, this is the region 3. So, this is a potential barrier. I hope you understand what I mean by potential barrier. The simplest thing is when you think of an automobile which encounters or comes across a speed breaker, the speed breaker is a potential barrier for the automobile. Similarly, here for the particle, the electrostatic potential, it is a number of positive ions or number of negative ions which it has to overcome. The electrostatic potential leads to the potential barrier. On the other hand, you may have potential well. I told you what a well, water in a well is an example of a well. You ask the question, how are you? You say you are well, you are, or you are in the well, whether you are also, I am also in the same well, right. So, what do you mean by well? Well is the classical well is the well that you see in all the houses where you got water in a well. You know, water will not be able to come out of its own, it has to, you have to give energy, put a bucket and take the water out. So, similarly the electron in an atom or electron in a molecule or electron in a solid, they are all bound state systems, they are the examples for a potential well, wherein the potential is due to electrostatic potential. It is a, similarly a nucleon in a nucleus cannot come out. Nucleon may refer to either a proton or a neutron. The nucleon will not be able to come out of the nucleus of its own, you have to give energy. So, it is a nuclear potential. What is a potential well is something in, you got a particle here, the particle has to be taken out from the ground level. You have to assume this is a ground level, it is down the potential well. Now, this is a ground level, it is up, that is a potential barrier, right. The opposing potential is the potential barrier, the attractive potential is the potential well. For the minority carriers, as I told you, the presence of ionic layers act like potential wells, wherein you will understand if a minority carrier, namely electron, comes here, it will be attracted by the ions. The positive ions that you have got here, they will attract the electron. So, depending upon the number density, if you have got more number of positive ions, the attraction will be much larger. So, it depends upon the number. Similarly, if a hole were to come here, it will be again attracted by the collection of negative ions. So, the minority carrier currents will be simply proportional to the number density of ionic layers on each side. Okay. This is point important. Now, therefore, I will write down now the expressions for I 3 and I 4 will follow this kind of equations, wherein I 3 is proportional to the number density of particles on the p side. How many ionic layers are there, right? The number of minority carriers that you have, they all of them will be attracted, right. This gives the number of minority carriers. This is the p side, for the p is the electrons, the holes in the on the n side, right. Electron density on the p side, the hole density on the n side, the holes will be attracted, and the minority carriers, as I told you, will be attracted by the ions of the opposite type. Therefore, the currents will be simply directly proportional to the number density, whatever number of electrons are there, they will be attracted by the positive ions. Similarly, the holes will be attracted by the negative ionic layers. Okay. The presence of negative ionic layers or the positive ionic layers, they act like potential wells for the respective carriers. So, the currents I 3 and I 4 will be directly proportional to the number of electrons or the number of holes that you have got on the p side and n side respectively. So, p n and n p are the electron and the hole concentrations on the p and n side. So, the p side they are the number of electrons, on the n side the number of holes. Therefore, depending upon the number density, the current will simply proportional to the number density. So, C 3 and C 4 are again the constants. Now, we have to write down the sum of all the things, right. The currents under equilibrium condition, you have to find out the current I is equal to I 1 plus I 2 plus I 3 plus I 4. Okay. Let me write down now the current that you have here, assuming the C to flow, the current to flow from P to N side as positive, and the other one will be negative. So, I will be equal to C 1 times P p e to the power minus e theta naught by k t plus C 2 times n n e to the power minus e theta naught by k t minus C 3 into n p minus C 4 into P n. Okay. That is equal to 0, because I am not biased. So, mathematically speaking, the total current that will be flowing across the P n junction will be equal to 0. This can be now written you can take down the terms on the with the negative sign to the right hand side. So, that I can write these two terms to be equal to these two terms, right. So, you take the terms to the right hand side, okay. That is what you have as of now. Now, what is it going to do? Now, the PN junction is not simply kept, you have to apply a bias, you apply what you call a forward bias. That means, you take the p type the PN junction, apply a positive potential to the p side and negative potential to the n side. Okay. Now, you have the PN junction, you have a voltage, right. You apply a positive potential to the p side and negative potential to the n side. What will happen to the width of the junction? Now, tell me what will happen to width of the junction. Now, if you apply the positive potential, what will happen to the holes? The holes are positive charged particles. So, you apply a positive potential. Now, this positive potential repel the holes, it will make the holes to move in this direction towards the junction region. So, this hole will neutralize the negative ions. Similarly, the n side will be negatively biased. So, n will be this will become negative. So, it will repel the electrons will neutralize the positive ions. So, the width of the PN junction will decrease. What I would like to tell you now, when you forward bias a PN junction, the width of the PN junction will reduce. If the width decreases means what? What will happen to potential barrier? Because instead of 2 layers which the particle has to overcome, now supposing you say that the hole has moved and come here, then the width would have become narrow. So, the width of the PN junction depends upon the biasing, right. Let us now pass on to the summary part. The width of the PN junction, you should know, depends upon the number density of the impurity atoms. The junction width will become very narrow if the doping concentrations are increased on either side. Then ultimately we have to obtain what is called the rectifier equation. You have the question number 1, what happens if the two sides are heavily doped? Whether the PN junction will extend to the same extent on either side. With these two questions, we come to the end of the lecture number 14. The remaining things we will see in the next lecture. Thank you.